Hi everyone! Last week we discussed that it is possible for us researchers to simultaneously study more than one dependent variable. This is what we call a multivariate design. Not only will this save us time and resources, but it allows us to discover the influence of a factor on a combination of related outcomes. For example, parenting style not only influences moral reasoning among children or adolescents, it is also related to pro-social behavior such as sharing and helping. As moral reasoning and pro-social behavior are theoretically related to each other, it would be more meaningful to study them together. One way to analyze data from a multivariate design is through MANOVA, which stands for Multivariate Analysis of Variance. From the name itself, you can already guess that this is an extension of ANOVA. MANOVA tests for the linear composite or vector of the means between the groups of the independent variable. It combines two or more dependent variables to form a new dependent variable in such a way as to maximize the differences between the groups of the independent variable. It is between this new composite variable that you test for statistically significant differences between the groups. MANOVA is used to test the null hypothesis that there are no differences among the groups being compared in terms of the combination of the dependent variables. Statistically, we are comparing mean vectors instead of just one mean. A mean vector is a collection of the means of each of the dependent variables. In our example, it is hypothesized that adolescents will differ in moral reasoning and pro-social behavior depending on the parenting style that they experience growing up. As with any parametric test, there are assumptions that need to be met for MANOVA to work as it should. Otherwise, we need to choose a different test or find more robust alternatives. The assumptions of MANOVA include the basic assumptions of ANOVA, plus some extra ones. We'll go through each one briefly. The first three need to be considered when planning the design. In terms of independence, each observation must be independent, that is, not influenced by other entries in the dataset, regardless if it's from the same person or not. So how do we ensure this? Use random selection and random assignment, as well as counterbalancing measures when appropriate. In fact, random sampling is another requirement as it will help ensure other assumptions such as normality and homogeneity of variances. This assumption is especially applicable for experimental studies, where the independent variable is manipulated, as it will help establish causality. However, in studies where the predictor variable is a pre-existing characteristic, such as parenting style, we can forego this assumption. However, note that we cannot infer causality in such case. The independent variable must be categorical. If the IV or predictor is continuous, regression is a more appropriate analysis, which you will learn in Sci 202. The dependent variable must be continuous. For the example earlier, parenting style is categorized as authoritarian, authoritative, and permissive. The dependent variables, moral reasoning, and pro-social behavior were both measured using questionnaires, which produced scores at an interval level. The next three assumptions can be tested using SPSS or other statistical software once data has been collected. Before we proceed with the remaining 3 assumptions, we need to make sure first that data is encoded properly. Make sure that your variables are named properly and that the decimal places covers all the values possible for each of the variable. You may use the label column to have the full name of each of the variables so that it would help with the interpretation. Assign the respective values for variables which has categories. For instance, sex, or in terms of the parenting styles. And then make sure that the scale of measurement are assigned properly. In terms of the data, make sure that you have all the entries here encoded properly. So you have here the participant number, some demographic information, the independent variable. Actually, for this data set, I have 2, but for the purpose of this discussion, we will only be focusing on parenting style of the mother. And then we have our 2 dependent variables, moral reasoning and prosocial behavior. As I mentioned, the 3 remaining assumptions can be tested once data has been collected. So we have linear correlation, normality, and the assumption of homogeneity of variances and covariances. The assumption of linear correlation means 2 things. One is that the change in each dependent variable is linear across all conditions. The other is that the dependent variables must be moderately correlated to each other. We can check the shape of the relationship, whether it's linear or not, by examining the pattern of the scores. This can be done using graphs. Go to Graphs, and then choose Scatter Dot in Scatter Matrix. Place the dependent variables into the matrix variables box, and then choose the independent variable and place it to either columns or rows. I'll choose columns. Okay. We don't need to change any of the settings. Click OK. And then you have your scatter matrix. So we only need to check either the one on the upper right or the one on the lower left. So let's say we pick the one on the upper right. This scatter plot here represents the distribution of the scores of each participant in terms of moral reasoning and prosocial behavior for every parenting style. So 1 dot here represents 1 participant. In this case, this is a participant with an authoritarian parent, and this is the score for moral reasoning and for prosocial behavior. What we are looking for is an elliptical pattern, generally moving from bottom left to upper right. Now, to check if the dependent variables are moderately correlated, we need to run bivariate correlation using Pearson's R. To do this, we go to Analyze, Correlate, Bivariate. And then we choose our two dependent variables and place them under the variables box. We select Pearson's. Actually, that's already pre-selected. And then we can also have the means and standard deviations. Okay. Essentially, there's not much that needs to be changed. Click OK. And then you have here the correlations. So you have here the descriptive statistics, the means and standard deviation for each of your dependent variable. This represents the overall means for the entire sample. The Pearson correlation here, which is represented by letter R, represents the strength and direction of the relationship between two continuous variables. The R coefficient can range from 0 to 1 and can be positive or negative. 0 means no relationship and 1 means perfect relationship. Positive means that the variables move in the same direction. When one increases, the other increases as well, and vice versa. A negative coefficient means that the variables move in opposite directions. When one increases, the other decreases, and vice versa. For the purpose of testing the assumption of linear correlation, we need to evaluate the absolute value, meaning regardless of the sign or valence. As a rule of thumb, we want the correlation to be statistically significant and for our coefficient to range from 0.2 to 0.9. Some sources say 0.3 to 0.9, while others range from 0.2 to 0.8. As a compromise, let's follow the 0.2 to 0.9 range. We want to see if the dependent variables are correlated. Otherwise, it doesn't make sense to use MANOVA. We also don't want the dependent variables to be highly correlated. If two variables are highly correlated, they might as well be measuring the same thing. Statistically, this will limit the values of the results. If two or more dependent variables have high correlation, you can either combine the scores into one or choose one and drop the others from the analysis. For our example here, we have a positive correlation, and it's within the range for moderate strength of correlation, so 0.785. So that means we can proceed with MANOVA, or at least we've met the assumption of linear correlation. The next assumption is multivariate normality. In univariate ANOVA, this meant that the residuals come from a normally distributed sampling distribution. In multivariate models, the residuals of the combination of the dependent variables are assumed to come from a normally distributed sampling distribution. Multivariate normality, however, cannot be tested in SPSS. Instead, we can check the assumption of univariate normality as we did in a regular ANOVA. Analyze, then explore. So choose the dependent variables and place them under dependent list, and then choose your independent variable and place it under factor list. For plots, we would uncheck this one just so we don't clutter our output, and then check the normality plots with tests. Then OK. So let's see. In terms of normality, we know that we are looking for a non-significant result. A non-significant result means that the distribution is not significantly different from a normal distribution. And a significant result means that the distribution is significantly different from a normal distribution. So in this case, as we can see, for moral reasoning, it's normally distributed for authoritarian group, but not for authoritative and permissive. In terms of pro-social behavior, the authoritarian and authoritative group are normally distributed, but not permissive group. So remember that univariate normality is a necessary condition for multivariate normality, but it doesn't guarantee multivariate normality. Even so, testing for univariate normality using our sample data is just an estimation because we do not have access to the sampling distribution. Thus, violation of normality based on raw scores, such as in our example here, is often ignored as it is assumed that most of the variables that we study in psychology come from a normally distributed sampling distribution, even if our data is not. Also, the central limit theorem kicks in for as long as we have enough sample. So, proceed with the analysis, but make sure to clearly report any violation for the readers to make their own decision when evaluating our findings. The final assumption pertaining to the homogeneity of variances and covariances can be tested when we run MANOVA. So let me first show you the process of running MANOVA before we go into the last assumption. To run MANOVA, go to Analyze, General Linear Model, and then choose Multivariate. Okay. Select your dependent variables and move them to the dependent variables box, and then choose your independent variable and place it under fixed factors. Essentially, all the choices that we choose here would be similar to running a one-way independent ANOVA. First, click Options and select Descriptive Statistics, Estimates of Effect Size, and the homogeneity test option here tests for univariate homogeneity of variances. We might need this later if the MANOVA or the multivariate effect is found to be significant. Okay. And then we might need post hoc also later on. Remember that post hoc is for the univariate effect, and we will only interpret univariate effect if there is a significant MANOVA. But in case it's significant, then at least we have this option. So I will choose one test for if the variances are equal, and another test for when the variances are not equal, just so we don't have to rerun MANOVA once we find whether or not the homogeneity of variances for the univariate effect is significant. Click Continue, and then for marginal means, we choose Bonferroni for comparing the main effects. And then, what else? I think that's it. And then click OK. We have our between subjects factor shown here. We only have one, so it's parenting style. And we have three groups: authoritarian, authoritative, and permissive. Then we have our descriptive statistics, although we would likely use the estimates table because it has the confidence intervals. Now, before we interpret any of the remaining tables, we first need to check for the remaining, or rather the last assumption, which is the assumption of homogeneity of variances and covariances, or also labeled as homogeneity of covariance matrices. In univariate models, we have the homogeneity of variances. In multivariate models, we are checking for the homogeneity of the variances as well as the covariances. Covariances refer to the correlation between any two dependent variables, and we assume that the correlation is the same in all of the groups that are being compared. A large variance and covariance is often a product of having a small sample, and this will lead to a distorted p-value. To test for the assumption of homogeneity of variances and covariances, SPSS produces the boxes M. Just like Levine's test of homogeneity of variances, we want this test to be not significant. However, boxes M test is highly sensitive, so we set the significance criteria at 0.001 instead of 0.05. That means values that are equal to or less than 0.001 are considered as statistically significant, which in our example here shows that yes, it seems like our variances and covariances are significantly different from each other. However, if sample sizes are equal, which in our case here, so we have equal sample sizes, researchers tend to disregard the boxes test because it tends to be unstable, and we can also use robust MANOVA statistics such as Hotelling's T and Peele's statistics. If sample sizes are not equal, robustness cannot be assumed. The greater the difference in sample sizes and the more outcome variables measured in the analysis, the more distorted the p-values become. However, SPSS doesn't provide a robust alternative for unequal sample size. Thus, try as much as possible to have equal sample sizes and limit the number of outcome variables to less than 10. So, given that we have the same sample sizes, even if the assumption of homogeneity of variances and covariances was violated, we can still proceed with the MANOVA. Now, let's move on to the main analysis. Remember that when running MANOVA, we are most interested in the multivariate effect, that is, the effect of the independent variable on the combined dependent variables. SPSS produces 4 multivariate test statistics. You have Peele's trace. This is often favored for unequal sample sizes and when the assumption of homogeneity of covariance matrices is not met. Wilks lambda is commonly used and is a good option when the variances are not equal. Wilks lambda varies from 0 to 1, and a value of 0 indicates that the group's mean vectors differ, and 1 shows that the group's means vectors are the same. Hotelling's trace is another choice when the assumption of homogeneity of covariance matrices is not met. The last choice is Roy's largest root, which is conceptually the same as the univariate F statistic. Often, the F value that it produces will be higher than the others, and it will tend to produce a lower P value, making it at times statistically significant when others are not. This is because it has higher power, meaning lower risk for type 2 error. However, researchers tend to err on the side of caution and thus choose Wilks lambda. But note that in our case, because the assumption of homogeneity of covariance matrices was not met, we will report Pillai's trace. If we only had 2 levels of the independent variable, all 4 tests will produce identical results. But in our case, we have 3 levels of our independent variable. For our result, parenting style of mother has a significant multivariate effect on moral reasoning and prosocial behavior. The Pillai's trace value is 0.546, and this is our F statistic. And our degrees of freedom, this is the between subject degrees of freedom, and this is our DF for our residual, or the numerator, or the within subject or within groups degree of freedom. And then this is our P value, which is lower than our alpha 0.05, and we have our effect size at 0.273. MANOVA is an omnibus test. Thus, it doesn't tell us exactly what combinations of the scores of the dependent variables distinguish one group from another. It only tells us that there is a difference, just like any other ANOVA. To know exactly how the groups differ in the combined dependent variables, we need to run discriminant analysis. However, this is beyond the course. Andy Field discusses this in Chapter 17. Another option is to interpret the univariate F tests only if the multivariate effect was significant. So aside from the multivariate test, MANOVA also produces the univariate effect. In fact, there are 2 tables that shows the univariate effect. So you have here tests of between subjects effects and our univariate tests. You can choose to interpret from this table or the one here. They should have the same values. Just make sure that you look at the correct row for the independent variable. So the univariate tests tells us of the univariate effect of the independent variable on each of the dependent variable. So as you see here, this is our independent variable, and these are the dependent variables that are now separated, and you get a separate F and P value for each of the dependent variable. But just like what you learned from when we run a post hoc analysis, when you do several tests, in this case, we are running 2 separate univariate tests to test each dependent variable. This will increase the risk of type 1 error. But the MANOVA result that is presented, or rather the ANOVA table that is presented here by SPSS, doesn't adjust for that increase in type 1 error, and so we have to manually apply the Bonferroni method of adjusting for type 1 error. To adjust, divide the alpha by the number of dependent variables. There are other methods, but this is the simplest one. This value is our new alpha. This means that we will only say there is a statistically significant difference if the p-value is equal to or lower than the new alpha, in this case 0.025. Let's see what our findings, what the results tell us. Maternal parenting style seem to have a significant univariate effect on moral reasoning as well as on prosocial behavior. So we have here the F statistic for each dependent variable, and then the corresponding p-value and the effect size. So you have here the degree of freedom, the numerator degree of freedom, and then the error degree of freedom, or the denominator degree of freedom. If the univariate ANOVA result is significant, just like here, interpret the post hoc results. But first, check the Levene's test if homogeneity of variances was met. This is an assumption we need to check since we are essentially looking at the univariate ANOVA. Based on the results, choose the appropriate post hoc, whether Bonferroni or Games-Howell. So here, moral reasoning based on the Levene's test doesn't have homogeneous variances. Prosocial behavior has homogeneous variances. So that means that for moral reasoning, we need to use Games-Howell. For prosocial behavior, we can use Bonferroni. So look for the post hoc results here. Okay. So I know SPSS is a bit cluttered with all of the different extra rows that actually is just a mirror of other rows. Make sure that you check the correct row. Okay. So when interpreting post hoc, remember that we still need to adjust the alpha value to 0.025 instead of 0.05. In this case, let's see, for moral reasoning, we need to use Games-Howell. So that means here, authoritarian versus authoritative. Yes, it's significant. Authoritarian versus permissive. The difference is also significant. And then we have authoritative versus permissive, and the difference is also significant. In terms of prosocial behavior, we can use Bonferroni. So authoritarian versus authoritative is significantly different. Authoritarian versus permissive also, it's not significant. And authoritative versus permissive is significant. As an additional reminder, univariate statistics results may not be significant even if the multivariate effect was. This is because they are testing for different outcomes. Just like how you can find a significant ANOVA result but not a significant post hoc.